I assume you from high school you know how to add and multiply complex numbers using the relation I squared equals -1. I'm a little less certain that you remember how to divide them. I hope you read last night by way of preparation for that, but since that's something we're going to have to do a lot of in differential equations. So remember that the division is done by making use of the complex conjugate. So if z is equal to a plus bi, some people write a plus ib, and sometimes I'll do that too if it's more convenient. Then the complex conjugate is what you get by changing I to -I. And the important thing is that the product of those two is a real number. The product of these is a squared minus the quantity ib all squared, which makes a squared plus p squared, because I squared is -1. So the product of those, that's what you multiply. If you want to multiply this by something to make it real, you always multiply it by its complex conjugate. And that's the trick that underlines the doing of division, so that, for example, I better hang on to these since I'll never remember all the examples that I've made. Suppose, for example, we wanted to calculate 2 plus I divided by 1 minus 3I. Another calculate, it means I want to do the division. I want to express the answer as in the form a plus bi. What you would do is multiply the top and bottom by the complex conjugate of the denominator in order to make it real. So it's 1 plus 3i divided by 1 plus 3i, as they taught you in elementary school. That is 1 in a rather odd notation, and therefore multiplying by it doesn't change the value of the fraction. And so the denominator now becomes 1 squared plus 3 squared, which is 10, and the numerator is, learn to do this without multiplying out 4 terms. You must be able to do this in your head, and you always do it by the grouping or post office method, whatever you want to call it. Namely, first put down the real part, which is made out of 2 times 1 minus 3 times 1, so that's -1. And then the imaginary part, which is I times 1, that's 1, coefficient 1, plus 6I, so that makes 7I. Now, some people feel this still doesn't look right. If you wish, and for some places in differential equation, it'll be useful to write that as minus 1/10 plus 7/10 I. And now it's perfectly clear that it's in the form a plus bi. So learn to do that. If you don't know already, it's going to be important. Now, the main thing today is the polar representation, which sometimes they don't get to in high school. And if they do, it's usually not in a grown-up enough form for us to be able to use it. So I have to worry about that a little bit. The polar representation, of course, is nominally just the switch to polar coordinates. If here's a plus bi, then this is r, and that's theta, and therefore this can be written as, in the polar form, that would be r cosine theta plus I plus r cosine theta. That's the a part. And the b part is, the imaginary part is r sine theta times I. Now, it would be customary at this point to put the I in front, just because it looks better. The complex numbers are commutative, satisfy the commutative law of multiplication, which means it doesn't matter in multiplication whether you put I in front or behind. It's still the same answer. So this would be r cosine theta plus I times r sine theta, which of course will factor out and make it cosine theta plus I sine theta. Now, it was Euler who took the decisive step and said, hey, look, I'm going to call that e to the I theta. Now, why did he do that? Well, because everything seemed to indicate that it should. But that's certainly worth the best color we have, which is what? Getting low here. Okay. Nonetheless, it's worth pink. I'll even give him his due, Euler. Sometimes it's called Euler's formula, but it really shouldn't be. It's not a formula, it's a definition. So in some sense, you can't argue with it. He said, well, if you want to call putting a complex number in a power and calling it that, you can, but one can certainly ask why he did it, and the answer, I guess, is that all the evidence seemed to point to the fact that it was the thing to do. Now, I think it's important to talk about that a little bit because it's, in my opinion, if you're seeing this for the first time, even if you read about it last night, it's a mysterious thing, and one needs to see it from every possible point of view. It's something you get used to. You will never see it in a sudden flash of insight. It'll just get as familiar to you as more common arithmetic and algebraic and calculus processes are. But look, what is it we demand? If you're going to call something an exponential, what is it we want an exponential to do? What gives something the right, an expression like this, the right to be called e to the I theta? The answer is I can't creep inside Euler's mind. It must have been a very big day in his life. He had a lot of big days, but when he realized that that was the thing to write down as the definition of e to the I theta. But what is it one wants of an exponential? Well, the high school answer surely is you want it to satisfy the exponential law. Now, to my shock, I realize a lot of people don't know. In my analysis class, these are some math majors or graduate engineers in various subjects, and if I say prove such and such using the exponential law, I'm sure to get at least half a dozen emails asking me, what's the exponential law? Okay, the exponential law is a to the x times a to the y equals a to the x plus y. The law of exponents. That's the most important reason why that's the single most important thing about exponents and the way one uses them. And this is the exponential function called the exponential function because because all the significant stuff is in the exponents. All right, so it should satisfy, we want, first of all, the exponential law to be true. But that's not all. That's a high school answer. An MIT answer would be, what is the role of, why is e to the x such a popular function? Well, of course, it does satisfy the exponential law, but for us, an even more reasonable thing, it's the function which, when you differentiate it, you get the same thing you started with. And it's, apart from a constant factor, the only such function. Now, in terms of differential equations, it means that it's the solution that e to the, let's be a little generous, make it e to the ax. No, better not to use x, because x, complex numbers tend to be called x plus iy. Let's use t as a more neutral variable, which is standing outside the fray, as it were. It satisfies the relationship that it's the solution, if you like, to the differential equation. That's a fancy way of saying it. dy dt equals a times y. Now, of course, that is not unique. We could make it unique by putting an initial value. So if I want to get this function and not a constant times it, I should make this an initial value problem and say that y of 0 should be 1. And now I will get only the function e to the at. So in other words, that characterizes this function. It's the only function in the whole world which has that property. Now, if you're going to call something e to the I theta, it should have, we want that to be true. So here are my questions. Is it true that e to the I theta 1, let's use that, times e to the I theta 2? Oh, I see I'm on a collision course here, but that's easily fixed. Is that equal to e to the I theta 1 plus theta 2? If that turns out to be so, that's a big step. What would we like to be true here? Well, will it be true that the derivative with respect to t of e to the I theta, I would like that to be equal to I times e to the I theta. So, question? Question. I think those are the two most significant things. Now, the notes do a third thing, talk about infinite series. Since we haven't done infinite series, it's not officially part of the syllabus, the kind of power series that are required, but I will put it down for the sake of completeness, as people like to say. So it should behave right with the infinite series should be nice. Infinite series should work out, should be, there is no word for this, should work out, let's say. And what's the little music? Is that some weird music I hear, or is it only me that hears it? Yes, Lord. Somebody up there, I feel I'm being watched up there. This is terrible. So there's one guy, here's another guy. And I won't put a box around the infinite series since I'm not going to say anything about it. Okay, now these things in fact are both true, otherwise why would I be saying them and why would Euler have made the formula? But what's interesting to see is what's behind them. And that gives you a little practice also in calculating with the complex numbers. So let's look at the first one. What will it say? It is asking the question, it says, please calculate the product of these two things. Okay, I do it, I am told. I will calculate the product of cosine theta 1 plus I cosine theta 2 sine. Sine theta 1. That's e to the I theta 1, right? So that corresponds to this. The other factor times the other factor, cosine theta 2 plus I sine theta 2. Okay, what does that come out to be? Well, again, we'll use the method of grouping. What's the real part of it? The real part of it is cosine theta 1, cosine theta 2. And then there's a real part which comes from these two factors. It's going to occur with a minus sign because of the I squared, and what's left is sine theta 1, sine theta 2. And then the imaginary part, I'll factor out the I, and then what's left I won't have to keep repeating the I. So it will be sine theta 1 cosine theta 2. And the other factor will be cosine theta 1 sine theta 2 plus sine theta 2 cosine theta 1. Well, it looks like a mess, but again, high school to the rescue. What is this? The top thing is nothing in disguise, but is a disguised form of cosine of theta 1 plus theta 2. And the bottom is sine of theta 1 plus theta 2. So the product of these two things is this, and that's exactly the formula. In other words, this formula is a way of writing those two trigonometric identities for the cosine of the sum and the sine of a sum, instead of the two identities taking up that much space, written one after the other, they take up this much space, and they say exactly the same thing. Those two trigonometric identities are exactly the same as saying that e to the I theta satisfies the exponential law. Now, that's, people ask, what's beautiful in mathematics? To me, that's beautiful. I think that's great. Something long turns into something short, and it's just as good, and moreover connects with all these other things in the world, differential equations, infinite series, blah, 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 blah. Okay. I don't have to sell Euler. He sells himself. Now, how about the other one? Now, that's obviously something has been, I haven't said something because for one thing, how do you differentiate? If there's theta here and t down there, how do I look? Okay, that's easily fixed. But how do I differentiate this? What kind of a guy is e to the I theta? Well, if I write it out, take a look at what it is. It's cosine theta plus I sine theta. As theta varies, it's a function. The variable is real. Theta is a real variable. It's the angle in radians, but it runs from negative infinity to infinity. So if you think of functions as a black box, what's going in is a real number, but what's coming out is a complex number. So schematically, if here's the I theta box, and you like to think that way, theta goes in, and that's real, and a complex number, this particular complex number, comes out. So one would call it, I'm not going to write this down because it's sort of pompous and takes too long, but it is a complex valued function of a real variable. You got that? Up to now, we studied real functions of real variables, but now real valued functions of real variables, those are the kind calculus is concerned with, but now it's a complex valued function because the variable is real, but the output, the value of the function, is a complex number. Now, in general, such a function, well, maybe I better say complex valued, how about complex valued function of a real variable. Let's change the name of the variable. T is always a real variable. I don't think we have complex time yet, although I'm sure there will be someday when the next Einstein appears. Complex valued function of a real variable, T, in general, would look like this. T goes in, and what comes out? Well, a complex number, which I would then have to write this way. In other words, the real part depends on T, and the imaginary part depends upon T. So a general function looks like this. A general complex valued function. This is just a special case of it, where the variable has a different name, but the first function would be cosine T, and the second function would be sine T. So my only question is, how do you differentiate such a thing? Well, I'm not going to fuss over this. One could go, the general definition is, and with deltas and whatnot, but the end result of a perfectly fine definition is you differentiate it by differentiating each component. The reason you don't have to work so very hard is because this is a real variable, and I already know what it means to differentiate a function of a real variable. So I can write it this way, that the derivative of u plus iv, I'll abbreviate it that way. This means the derivative with respect to whatever the variable, since I didn't tell you what the variable in these functions was, I don't have to tell you what I'm differentiating with respect to. It's whatever was there that you can't see. And the answer is, it will be the derivative of u plus I times the derivative of v. You differentiate it just the way you would if these were the components of a motion vector. You would get the velocity by differentiating each component separately. And that's what you're doing here. Okay, now the importance of that is that it at least tells me what it is I have to check when I check this formula. But so let's do it now that we know what this is. We know how to differentiate the function. Let's actually differentiate it. That's fortunately by far the easiest part of the whole process. So let's do it. So what's the derivative? Let's go back to t, our generic variable. I want to emphasize that these are that these functions, when we write them as functions, the theta will almost never be the variable outside of these notes on complex numbers. It'll normally be time or something like that, or x, a neutral variable like x. So what's the derivative of e to the I theta? I'm hoping that it will turn out to be I e to the I theta, and that the yellow law may be true just as the green one was. Okay, let's calculate it. It's the derivative with respect... Unfortunately, I can convert t's to thetas, but not thetas to t's. C'est la vie. Okay. Times cosine t plus I sine t. And what's that? Well, the derivative of cosine t, differentiating the real and imaginary parts separately and adding them up. It's negative sine t plus I times cosine t. Now, let's factor out at the I, because it says, if I factor out the I, what do I get? Well, now the real part of what's left will be cosine t. And how about the imaginary part? You see, it will be I sine t, because I times I is gives me that negative 1. And what's that? E to the it. I times e to the it. So that works too. What about the initial condition? No problem. What is y of 0? What's the function at 0? Well, don't say right away, I times 0 is 0, so it must be 1. That's illegal because... And why is that illegal? It's because you're not exactly in that formula, you're not multiplying I times theta. I mean, sort of you are, but that formula is the meaning of e to the I theta. Now, it will be very nice if this is like well, you can't do, anyway, you can't do that. So you have to do it by saying it's the cosine of 0 plus I times the sine of 0. And how much is that? This is the sine of 0 is 0. Now it's okay to say I times 0 is 0, because that's the way complex numbers multiply. What is the cosine of 0? That's 1. So the answer indeed turns out to be 1. So this checks really from every conceivable standpoint, and as I indicated, also from the standpoint of infinite series. So we're definitely allowed to use this. Now, the more general exponential law is true. I'm not going to say much about it. So in other words, e to the a, this is really a definition. E to the a plus ib is going to be, in order that the general exponential law be true, this is really a definition. It's e to the a times e to the ib. Now notice, when I look at and any complex number, so in terms of this, the polar form of a complex number, to draw the little picture again, if here's our complex number, and here is r, and here's the angle theta, so the nice way to write this complex number is as r e to the I theta. The e to the I theta is, and now why is that? What is the magnitude of this? This is r, the length of the absolute value. That has That, I didn't talk about magnitude and argument. That's what I guess I should have, but it's in the notes. And all right, so R is called the modulus. Well, the fancy word is the modulus. And we haven't given the complex number a name. Let's call it alpha. Modulus of alpha. And theta is called, it's the angle. It's called the argument. I didn't make up these words. They're from a tradition of English that has long since vanished. When I was a kid and you wanted to know what a play was about, you looked in the playbill and it said, the argument of the play. It's that kind of, it's that old-fashioned use of the word argument. Argument means the angle. And sometimes that's abbreviated by arg alpha. And this is abbreviated, of course, as the absolute value of alpha, its length. Okay, the notes give you a little practice changing things to polar form. I think we will skip that in favor of doing a couple of more other things, because that's pretty easy. But you should at least realize when you should look at polar form. The great advantage of polar form is particularly once you've mastered the exponential law, the great advantage of polar form is it's good for multiplication. Now, of course, you know how to multiply complex numbers even when they're in the Cartesian form. You know, that's the first thing you learn in high school, how to multiply a plus bi times c plus di. But as you'll see, when push comes to shove, you'll see this very clearly on Friday. And that's, Friday, when we talk about trigonometric inputs to differential equations, that the changing to complex numbers makes all sorts of things easy to calculate, and the answers come out extremely clear, whereas if we had to do it any other way, it's a lot more work, and worst of all, when you finally slog through to the end, you feel you're none the wiser. It's good for multiplication because the product of so here's any number in its polar form. That's a general complex number. Its modulus times the e to the I theta times R2 e to the I theta 2. Well, you just multiply them as ordinary numbers. So the part out front will be R1, R2, and the e to the I theta's parts gets multiplied by the exponential law and becomes e to the I theta 1 plus theta 2, which makes very clear that to multiply geometrically two complex numbers, you multiply the moduli, the r's, the absolute values, how long the arrow is from 0 to the complex number, multiply the moduli, and add the argument. So the new number, its modulus is the product of R1 and R2, and its argument, its angle, polar angle, is the sum of the old two angles. And you add the angles. And you put down in your books angles, but I'm being photographed, so I'm going to write arguments. In other words, it makes the geometric content of multiplication clear in a sense in which this is extremely unclear. From this law, you know, blah, 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 whatever it turns out to be, you have not the slightest intuition that this is true about the complex numbers. It's that first thing is just a formula, whereas this thing is an insightful representation of complex multiplication. Now, I'd like to use it for something, but before we do that, let me just indicate how just the exponential notation enables you to do things in calculus, formulas that are impossible to remember from calculus. It makes them very easy to derive. A typical example of that is, suppose you want to, for example, integrate e to the negative x cosine x. Well, number one, you spend a few minutes running to a calculus textbook and trying to find out the answer because you know you're not going to remember how to do it. Or you run to a computer and type in MATLAB and something, or you fish out your little pocket calculator, which will give you a formula, and so on. So you have aids for doing that, but the way to do it, if you're on a desert island, and the way I always do it, because I never have any of these little aids around, and I cannot trust my memory. Probably a certain number of you remember how you did it in high school, or how you did it in 1801, if you took it here. You have to use integration by parts, but it's one of the tricky things that's not required on an exam, because you have to use integration by parts twice in the same direction, and then suddenly, by comparing the end product with the initial product and writing an equation, somehow the value falls out. Well, that's tricky. And it's not the sort of thing you can waste time stuffing into your head unless you're going to be in the integration bee during IAP or something like that. Instead, use complex numbers as the way to do this. How do I think of this? Cosine x. What I do is I think of that e to the negative x, cosine x, is the real part. The real part of what? Well, cosine x is the real part of e to the ix. So this thing, this is real. This is real too, but I'm thinking of it as the real part of e to the ix. Now, if I multiply these two together, this is going to turn out to be, therefore, the real part of e to the minus x. I'll write it out very pompously, and then I'll fix it. I would never write this, but you are you. Okay? It's e to the minus x times when I write cosine x plus I sine x, the real part of that is cosine x. So it's the real part of, write it this way, for real part of e to the, factor out the x, and what's up there is negative 1 plus I times x. Okay? And now, so the idea is the same thing is going to be true for the integral. This is going to be the real part of that, the integral of e to the minus 1 plus I times x dx. In other words, what you do is, this procedure is called complexifying the integral. Instead of looking at the original real problem, I'm going to turn it into a complex problem by turning this thing into a complex exponential. This is the real part of that complex exponential. Now, what's the advantage of doing that? Simple. It's because nothing is easier to integrate than an exponential. And though you may have some doubts as to whether the familiar laws work also with complex exponentials, I assure you they all do. It would be lovely to sit and prove them. On the other hand, I think after a while you'd find it rather dull. So I'm going to do the fun things and assume that they're true because they are. So what's the integral of e to the minus 1 plus I x dx? Well, if there is justice in heaven, it must be e to the minus 1 plus I times x divided by minus 1 plus I. Now, in some sense, that's the answer. It's not, does in fact give that. That's correct. I want the real part of this. I want the real part because that's the way the original problem was stated. I want the real part only. So I want the real part of this. Now, this is where what separates the girls from the women. This is why you have to know how to divide complex numbers. So watch how I find the real part. I write I write it this way, 1 over 1. I would skip, normally when I do the calculation for myself, I would skip a couple of these steps, but this time I'll write everything out. You're going to have to do this a lot in this course, by the way, both over the course of the next few weeks and especially toward the end of the term when we get into complex systems which involve complex numbers. There's a lot of this. So now is the time to learn to do it and to feel skillful at it. So it's this times e to the negative x times e to the ix, which is cosine x plus I sine x. Now, I'm not ready yet to do the calculation to find the real part because I don't like the way this looks. I want to go back to the thing I did right at the very beginning of the hour and turn it into an a plus bi type of complex number. In other words, what we have to do is the division. So the division is going to be, I multiply now I'm going to ask you to do it in your head. Well, I multiply the top and bottom by negative 1 minus I. What does that put in the denominator? 1 squared plus 1 squared, 2. And in the numerator, negative 1 minus I. This is the same as that. But now it looks in the form a plus bi. It's negative 1 over 2 minus I times 1/2. So this is multiplied by e to the x and cosine x. So if you're doing it and practice a little bit, please don't put in all these steps. Go from here, well, I would go from here to here by myself. Maybe you shouldn't. Practice a little before you do that. And now what do we do with this? Now this is in a form to pick out the real part. We want the real part of this. So you don't have to write the whole thing out as a complex. In other words, you don't have to do all the multiplications. You only have to find the real part of it, which is what? Well, the e to the negative x will be simply a factor. That's a real factor, which I don't have to worry about. And in that category, I can include the 2 also. So I only have to pick out the real part of this times that. And what's that? It's negative cosine x. And the other real part comes from the product of these two things. I times negative I is 1. And what's left is sine x. So that's the answer to the question. That's the integral of e to the negative x cosine x. Notice that it's a completely straightforward process. It doesn't involve any tricks. Unless you call going to the complex domain a trick, but I don't. It's just something that as soon as you see in this course the combination of e to ax times cosine bx or sine bx, you should immediately think, and you're going to get plenty of it in the couple of weeks after the exam, you're going to get plenty of it, and you should immediately think of passing to the complex domain. That will be the standard way we solve such problems. So you're going to get lots of practice doing this, but this was the first time. Now, I guess in the time remaining, I'm not going to talk about the notes IR at all, but I would like to talk a little bit about the extraction of the complex roots, since you have a problem about that. Because it's another beautiful application of this polar way of writing complex numbers. Suppose I want to calculate so the basic problem is to calculate the nth roots of 1. Now, in the real domain, of course, the answer is sometimes there's only one of these, one itself, and sometimes there are two, depending on whether n is an even number or an odd number. But in the complex domain, there are always n answers as complex numbers. 1 always has n nth roots. Now, where are they? Well, geometrically, it's easy to see where they are. Here's the unit circle. Here's the unit circle. One of the roots is right here at 1. Because 1's the end. Now, where are the others? Well, do you see that if I place, let's take n equal 5 because that's a nice dramatic number. If I place these at 5 equally spaced points around the unit circle, so in other words, this angle is alpha. Alpha should be the angle, what would be the expression for that? If there are 5 such equally spaced, it will be 1/5 of all the way around the circle. All the way around the circle is 2 pi, so it will be 1/5 of 2 pi in radians. Now, it's geometrically clear that those are the 5/5 roots. Because how do I multiply complex numbers? I multiply the moduli. Well, they all have moduli 1. So if I take this guy, let's call that complex number, I hate to give you, they're always given Greek notation. Well, all right, why not torture you? Zeta. At least you'll learn how to make a zeta in this period. Small zeta, so that's zeta. There's our 5th root of unity. It's the first one that occurs on the circle that isn't the trivial one, 1. Now, do you see that, how would I calculate zeta to the 5th? Well, if I write zeta in polar notation, what will it be? The modulus will be 1, and therefore it will be simply, the r will be 1 for it, because its length is 1, its modulus is 1. What's up here? I times that angle, and that angle is 2 pi over 5. So there's, just geometrically, I see where zeta is. And if I translate that geometry into the e to the I theta form for the formula, I see that it must be that number. Now, let's say somebody gives you that number and says, hey, is this a 5th root of 1? I forbid you to draw any pictures. What would you do? You say, well, I'll raise it to the 5th power. What's zeta to the 5th power? Well, it's e to the I 2 pi 5. And now if I think of raising that to the 5th power, by the exponential law, that's the same thing as putting a 5 in front of the exponent. So this times 5, now what's that? That's e to the I times 2 pi. And what's that? Well, it's the angle, if the angle is 2 pi, I've gone all the way around the circle and come back here again. I've got the number 1. So this is 1. Since the angle, the argument 2 pi is the same as an angle, is the same as the argument. Now, let's not write it that way. That's not. I have to. That's bad. No, it's wrong. It's just wrong. Since 2 pi and 0 are the same angle. So I can replace this by 0. Oh dear. Well, Okay, I have to stop right in the middle of things. So you're going to have to read a little bit about how to find roots in order to do that problem, and we'll go on from that point Friday.